Good evening. Today we are going to see nodes and elements in finite element method. Now, my channel, that is Civil Engineer Technical Hubs, and with playlist, we have different playlists related with different subject. Now, you subscribe Civil Engineers Technical Hub. Now already I mentioned we are going to see nodes and elements in this video related with finite element method or analysis. Now, what is node? Node actually a point in space, and which is defined by its coordinates. So we know if we have considered any point, if I will consider any point in xy plane, then this point will be defined by its coordinate. And in finite element, we are going to define degrees of freedom at all these points, which are known as nodes. So nodes, we are going to consider a point, and at that point, we are going to define the degrees of freedom. Then what is element? So the member connecting to these two nodes are known as element. Now we will use them in every analysis when we are going to perform finite element analysis, or when we are going to use finite element method. So these nodes and elements plays very important role. Now I will just explain once. So nodes. So we have actually two types of nodes. One we have that is external node, and second we have that is internal nodes. Now external nodes are on the boundary. So these are on the boundary. And internal nodes, these are inside the boundary. So this is on boundary. Now here again we are going to define two types. One we have primary, and second we have secondary. Now primary, these are always at corners or at ends, and secondary are between primary. So this is actually a short, we can say, the classification of nodes. Now I will show all these nodes, all these in this presentation. So now you can see we have this, there are two types of nodes, just we have seen. So we have external nodes and we have internal nodes. Now external nodes which occur, so I just mentioned, on the edge or surface of the element, then they are common to two or more elements. So these are at ends I have mentioned, or these are at corners. So end or corner. Now we can have two types. So these nodes are further classified, primary nodes, and these are at the ends of one-dimensional elements or at the corner of two-dimensional elements and three-dimensional elements. Now you can see node 1, 2, 3, you can see over here, these are at corners and are known as primary nodes. If you have line element, then you have primary nodes, these are at ends. So these I can mention it as 1, 2, these are your primary nodes. Now we have second type, that is secondary nodes, and these are along the side but between the primary nodes and are known as, or are shown by 4, 5, 6. So you can see these secondary nodes, we have 4, 5, 6. If I will consider a line element, so in this line element, we have this as 1, 2, which are primary nodes, and or I will make it red. So we can have this 1, 2. So I will mention this red 1, 2, and these we have primary nodes. And then we can use that is blue ink, and that will show you that is secondary nodes. So I can write this as 3, 4. So between primary nodes, we have secondary nodes. Then we have another type, internal nodes. So internal nodes are inside the element. These are specific to the element selected. Such nodes are selected to satisfy the requirement of geometric isotropy. So now this is related with your Pascal's triangles, and that we will see when we will go to these Pascal's triangles. But we have to keep in mind these are inside the element and or inside the boundaries. So now we know red we have primary, blue we have secondary, and now internal nodes. You can see here we have mentioned by green 7890. So we have these are the internal nodes. So we have these are the nodes types, that is external, internal, and then primary and secondary. Now similarly we have actually elements, and we are going to classify these elements again in 4 types. We have first one-dimensional element, then we have two-dimensional element, then we have isoparametric element, and then axisymmetric element. Isoparametric and axisymmetric. So we will see one by one all these 4 elements, but in brief we have to go with these 4 types. Now I will show you in detail in this presentation. So we have types of elements. These are, so what already I mentioned, we are going to divide this finite element model into small pieces, and those elements are called as finite element. Means model is divided into small parts, and that parts we are going to say as elements. This element connects all characteristic points that already we have shown, which are known as node, which lie on their circumference. Now we have 1D element, we have 2D element, 3D element, axisymmetric element. Actually in this we have isoparametric element also, that we will see. So different element classification you have to decide. So now we can go based on the shape of the elements. We have one-dimensional, we have two-dimensional, three-dimensional, and axisymmetric element. Now we will go with one-dimensional. When our problems, these are one-dimensional problem. One-dimensional means our 2 dimensions are very small compared with 3rd dimension. And generally, here we are going to consider as beam, we are going to consider as column whose cross-sectional dimension are small compared with their element. And in that case, we are going to consider one-dimensional element, which are known as line element. Now in this we have line element with 2 nodes, line element with 3 nodes. So we have 2 primary, 1 secondary. So likewise, we are going to consider number of nodes. If you are going to decrease the dimension of the element, then you will converge to the correct value. So as your nodes increases, your element becomes smaller one, and you will be close to your exact answer. Then we have 2-dimensional element. Now in this 2-dimensional element, you can see 2-dimensional elements are required to solve 2-dimensional problems. And here we can have this slab, we can have thin plate. So these are the members or models, I can say, or elements where we have 2-dimensional very large compared with your 3rd dimension. And in that case, the elements we have to consider, these are 2-dimensional elements. Now 2-dimensional element, we have 2 types, that is triangular element and rectangular element. Now in triangular element, we have first CST, and this is, you can have this, that is constant strain element or linear displacement element. Now in detail, you will understand when we will go for Pascal. So whenever you write any displacement function, then you have this as, so in this CST triangular element, if you will see triangular element, then you have 3 nodes. And whatever number of nodes you have, you have to consider one constant. Now, whenever you have these three nodes, we have to consider, so that you will understand when you will go to Pascal's triangle. So I have alpha 1 plus alpha 2x plus alpha 3y. So that you will understand from Pascal's triangle. But why we are going to say it as linear displacement? Because here you can see our displacement is proportional to x, which is power 1, or y to the power 1. And therefore it is linear displacement. If you will go for strain, then you can have dabba u by dabba x. Then we have that alpha 1 becomes 0, alpha 3y becomes 0, and then you can have this value as alpha 2, which is constant. So this is known as constant strain, and then you have that as linear displacement. So likewise, according to Pascal, when we will go to Pascal's triangle, I will explain that why we are going to say these elements, that is linear displacement or constant strain triangle. Then you can see we have, this will be CST element. We have three primary nodes only, no secondary nodes in CST element. Then we have second element where we have quadratic displacement, means your function, that is u, is proportional to x square or it is proportional to y square. And therefore it is quadratic triangle, or you can say, if you will see this, then you have known as linear strain. So when you will take derivative of this, then you are going to take, so one power will be reduced, it becomes twice x, and therefore it is linear strain and quadratic displacement triangle. Now in this, you can see we have 6 elements, 6 nodes. So we have 3 primary and 3 secondary nodes. And as we have 3 nodes in one line, so we are going to get it as quadratic displacement, and which will give us linear strain. So that we will see in constant strain when we will go in Pascal's triangle. Now QST, so that is one polynomial function of displacement that we are increasing. So here you have cubic displacement, and you can have this as quadratic strain. So that as you increase it, so now you can see here you have 3 primary nodes, and if you will see, you have 1, 2, 3, 4, 5, 6 secondary nodes, and you have also 1 internal nodes. So this is 10 noded triangular element. So 10 noded triangular element. First we have CST, 6 noded triangular element. Sorry, 3 noded triangular element. This LST we have 6 noded triangular elements. So we have elements like this. You can increase your displacement polynomial and means increase its polynomial value, and then automatically your polynomial function for strain also increases. So this name, this gives by your strain. So as polynomial function of strain increases, your this element name also changes. So we can have constant strain, linear, then quadratic, then you can have cubic. So likewise, this will increases. Then we have rectangular 2, that is when we have that element, a simple but less used 2-dimensional element is the 4-noded rectangular element. This system is easy to construct, but it is not well suited for inclined boundaries. So when we have inclined boundaries, then we are going to prefer that is triangular element. When it is rectangular boundaries, then we can go with this rectangular element. But we little come across these exact rectangular boundaries, and therefore we mostly prefer triangular element. So now in this, actually, we have 2 types. That is, one we have Lagrange rectangles, and second we have serendipity rectangles. So now you can see this. These we have only primary nodes. If you will go inside, then you have this as secondary nodes. If you will take again inside this boundary, then we have this as internal nodes. So now you can see this Lagrange rectangles. So these we are in the form of grid points. So you can see this is 6-noded rectangular element. This is 9-noded rectangular elements. This we have corner, we have primary, and between this we have secondary. Now that means here we have only external nodes. If we will go here, then we have external which are on the boundary. At corners we have primary, between primary we have secondary, and this we have internal nodes. So this is 9-noded rectangular element. And so if these are in the form of grids, so you can see we are in the form of grids. So these are known as Lagrange rectangular element. And this you can see we have 12-noded Lagrange rectangular element. Then we have serendipity rectangles. These are only on the boundaries. No internal nodes are present in case of serendipity. Means here we have only external nodes. And that we have, this will be same in both, you can see, but henceafter, whatever internal nodes, that will not be present in serendipity. So we can see likewise. So here we have only external nodes. No internal nodes are present in case of serendipity rectangles. Then we have quadrilateral element. So we are going to be with these as 2-dimensional, or we can say 3-dimensional. So these elements, you can see we have quadrilateral element. So we are going to be with 4 elements. In CST, we have 3 elements. So these quadrilateral, when we have these quadrilateral elements developed, or this concept of quadrilateral elements is developed, then we are not going to use triangular element because it is best suited for the boundaries. But after, again, this will be not satisfying the requirement of the boundaries. And then we have isoparametric concept. And this isoparametric concept means we are going to be with the elements which will be very close or as per our boundaries. And then these quadrilateral elements also not used nowadays. These are replaced by your isoparametric elements. And now that you can see how we have these isoparametric elements. So these elements, we are in this fashion. So we have these as curved boundaries, which can be fit with your curved boundaries. So elements, we have curved shape elements, which will be fit or suited for our curved boundaries. So you can see one possible solution to address the issue of stress concentration at corner nodes due to curved boundaries. And in that case, instead of straight edged elements, we will prefer these isoparametric elements. So curved elements are typically represented by higher ordered polynomial functions and such as quadratic or cubic polynomials, which allow for a more accurate approximation for the curved boundaries. And these isoparametric elements are developed, and these are going to be well suited for your curved boundaries or boundaries with higher order polynomials. So these are isoparametric elements. Then we have axisymmetric element. Now you can see this. These are the bodies which are symmetric with your axis. And when we have these bodies that symmetric with your axis, then in that case, it is preferable to use axisymmetric elements. And we can have these as axisymmetric elements, which will be useful for your bodies which are symmetric with your axis. So these are the different elements which we are going to use in your finite element method. Now, if you like this video, आवडला असेल तर लाईक करा आणि सबस्क्राईब करा सिव्हिल इंजिनियर्स टेक्निकल हब. So now we will stop here only. Thank you.